All right, in our last video, we left off on this slide and said that all nuclear reactions will release energy. So all nuclear reactions are exothermic. Now, the amount of mass that is lost is tiny. When you look at it, you would almost think it was insignificant. However, a tiny bit of mass lost, and I'm talking about like decimal places down, not whole numbers, a tiny bit of mass lost will correlate to a huge amount of energy. And this is why nuclear weapons are so much more destructive than regular bombs. All right, so I'm going to guess that you've probably heard of this equation before. E equals mc squared. So E stands for energy, which would be measured in joules or kilojoules. M is mass in kilograms. And C is the velocity or speed of light, which is 3 times 10 to the 8th meters per second. So if we lost an entire gram, which in our nuclear reactions, we're not losing an entire gram. It would be, fractions of that. But if we lost an entire gram and we plugged it into this equation, you will see that that would correlate to a huge amount of energy. Now, 1 gram, if we converted that to kilograms, would be 0.001 kilograms, because we would move the decimal place over 3 spots. Or if we want to use scientific notation, it would be 1 times 10 to the negative third kilograms. So that's how I'm going to plug it in. 1 times 10 to the negative third. Okay, C. Speed of light, 3 times 10 to the 8th. That's a big number. Light moves quickly. And then we're going to square that big number. So we got 1 times 10 to the negative third kilograms times 3 times 10 to the 8th squared. So 3 times 10 to the 8th squared would be 9 times 10 to the 16th. So then when we multiply those together, that would be 9 times 10 to the 13th joules. That is a lot of energy. So 1 gram would correlate with a massive amount of energy. Now, this particular calculation is not something that you will see on any of our tests or quizzes, but you do need to know that nuclear reactions release way more energy than a regular reaction, and this is the why. So I want you to at least have seen one example with that showing that a small amount of mass correlates with an insane amount of energy. All right, so what's actually happened in nuclear reactions when they lose this tiny bit of mass is, let's say that you're supposed to be producing a helium atom with a mass of 4. That would have 2 protons, 2 neutrons in it. So you could calculate what its mass actually would be down to like 6 decimal places, because you know the mass of a proton, so you would know the mass of 2 protons, you know the mass of a neutron, so you would know the mass of 2 neutrons. You add them up, and that would give you the predicted mass of helium. Then you get the actual mass, which is a tiny bit less. So there's this tiny bit of mass that's lost when the protons and neutrons combine. That's called the mass defect, that difference between what you think it should be based upon individual protons and neutrons and what it actually is. The larger the mass defect, the more mass has been converted to energy. So the larger the mass defect, the larger the amount of energy that you're releasing. All right, now we are going to specifically talk about fission and fusion. So, those are two big nuclear reactions that you need to have some knowledge of. So, fission is splitting apart. So, splitting apart a heavy nucleus to produce a lighter nuclei. Now, the most likely thing that you would see with fission is a neutron plus a uranium atom. So, a heavy atom, the uranium, is hit with a neutron and it splits apart into two lighter weight nuclei. Depending on exactly how the nucleus splits, you could get some different stuff, but the most common split makes barium, krypton, and three more neutrons. So in fission, we have a heavy atom, such as uranium. Actually, the only other thing other than uranium that's able to undergo fission is plutonium. So you have uranium or plutonium is hit with a neutron. That causes the uranium or plutonium to split apart, making two midweight nuclei, such as barium and krypton, and then additional neutrons. Those additional neutrons go on to hit additional uranium atoms, and then you get a chain reaction. So, this is the reaction that occurs in a nuclear power plant. And every single time this happens, a teeny, 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 teeny bit of mass is lost, but it's converted to a huge amount of energy. So, this is why nuclear power plants can produce a lot of energy from a smaller amount of fuel. This also was the reaction that did occur in the nuclear bomb, and we'll talk a little bit more about that later on. So, again, your most common example of fission is going to look like that. So uranium plus a neutron makes two midweight nuclei, and these could vary depending on the split, but krypton and barium is a very common split. More neutrons and a great deal of energy. The only other element that is capable of undergoing fission is plutonium. So you could also see this with plutonium. All right, then the neutrons that are given off can be reabsorbed by additional uraniums, and then we get to a chain reaction, and the reaction grows exponentially, and it can release a huge, huge, huge amount of energy. And this chain reaction occurs in nuclear power plants. So, one feature of the nuclear reactor is the control rods. The control rods absorb the neutrons, and depending upon the number of neutrons that they absorb, it will either slow the reaction or it can totally stop the reaction too. Because if you absorb all of the neutrons, then the reaction can't occur because the uranium is not going to undergo fission on its own. All right, so we are very briefly going to talk a teeny bit about nuclear power plants. First thing is, these structures here in the nuclear power plant, those are not the reactor. Those are the cooling towers. And what is being released here is steam. So steam, H2O gas, water vapor is coming out of the cooling towers. Once it hits the cooler air, then it recondenses. So the nuclear power plants, that's not smoke that's coming out of there, that is steam that is coming out of those cooling towers. All right, this is a very simplified diagram as to some of the parts of a nuclear power plant. So inside the containment structure, you would have the reactor. So this would be the reactor here. This little red box is where the fuel would be, which would be the uranium. The control rods are capable of absorbing neutrons to slow the reaction down or to even fully stop the reaction. The containment structure is made of very, very, very thick concrete. Usually the reactor is encased in steel, and then this is very thick concrete because remember, gamma radiation cannot penetrate concrete or steel. So, or lead. So that would help to hold in any radiation if there was a problem. So the fission reaction occurs, releases a great deal of energy, great deal of heat. That in turn boils the water, making steam, which powers the turbines, and that's where they get the energy from. They need a lot of water to cool the structure down and prevent it from overheating or having a nuclear meltdown. So water is continuously pumped through, kind of the same idea as like your radiator, where it pumps water through to absorb heat from your engine so it doesn't overheat. It's kind of the same thing. Water keeps getting pumped through to absorb the heat. And then you see the water vapor coming out of the cooling tower. Now, you're not going to need to, on a quiz, explain to me the functions and workings of a nuclear power plant. I just want to give you a little bit of general knowledge. So here is the cooling tower. That's the big identifiable structure. And then here, much smaller, would be inside there would be the reactor. It's encased in very thick concrete to help contain any radiation if there was a problem. All right, so nuclear power has some advantages and disadvantages. So you might be familiar with some nuclear accidents, such as the Fukushima power plant in Japan or Chernobyl in Ukraine. So you might be thinking, why would anybody ever have a nuclear power plant anywhere close to them? We have one relatively close to us. There's the Ginna nuclear power plant. That one is just east of Webster. So advantages for nuclear power is it is cheaper and more efficient. So you can get a lot more energy from a nuclear power plant, so therefore provides us with cheaper energy, which everybody always wants, a cheaper utility bill. And nuclear power can be cleaner than conventional fossil fuels. The main thing that nuclear power emits is the water vapor from the cooling towers. So it doesn't release any greenhouse gases that could lead to global warming, doesn't release any of the gases such as sulfur dioxide that contribute to acid rain. However, there's obviously some disadvantages. Now, everybody automatically goes down to this one here of some sort of nuclear accident. That is not very likely, but that's obviously a major, concern of people that live near a nuclear power plant. But the one that I really want to talk about is the daily disadvantage. So the byproducts of the reaction. So we have fission happening. So we're a neutron plus uranium makes two midweight nuclei, such as barium and krypton, and additional neutrons. So these that are produced are themselves radioactive. So that's a problem You have to figure out how to store and dispose those radioactive byproducts. They have very long half-lives. They stick around for a very long time, and since they're radioactive, you can't just ship them to your local landfill. So that is the daily problem with a nuclear power plant, is what to do with the essentially radioactive garbage. So a lot of times they bury them in huge storage containers, but as these decay naturally, they are exothermic and emit heat. So even those storage containers need to be cooled down to prevent them from overheating. And that's actually what happened in Fukushima. So that was earthquake occurred. When the earthquake occurred, there was a risk for tsunami. The power plant shut down. So the control rods went into the generators, turned all the generators off. So everything happened like it should. Then the tsunami came in, massive, caused a huge amount of damage, and took out the generators at the power plant. So with the generators out and the power out, the water that's supposed to cycle through to cool down the storage containers stopped cycling through, and they started to overheat and ended up exploding. So that's where their problem was not actually um, the actual reactor exploding, but the storage and disposal area did. And then those explosions, could then cause problems with the reactors too. So this is our daily disadvantage, is the storage and disposal of the waste product. And then of course, there's also the risk of some sort of nuclear accident, but can be more cost effective and because it's way more efficient. And as long as things are functioning properly, it can be cleaner than conventional fossil fuel. All right, as I talked about, two huge nuclear power disasters that you should just be somewhat familiar with to be an educated individual. Chernobyl was in the former Soviet Union, and that occurred in 1986. They were running a safety test late at night, and the fission reaction became uncontrolled in the reactor, so basically the chain reaction got out of control, leading to fires and explosions. Radiation was released into the air and spread, as far as Western Europe. And it's hard to pinpoint an actual number of deaths. There was a lot of deaths right afterwards of like the firefighters who went in to try to put out the fires, people in the surrounding area, people who worked at the power plant. But with the release of radiation, sometimes it's long term, like an increase in certain types of cancer, an increase in reproductive problems that then lead to infertility. So it's hard to pinpoint an exact number. There's a lot of great documentaries about Chernobyl. The HBO series is historical fiction, but it is well done and pretty historic. Fukushima is more recent. That was in 2011. Like I said, there was an earthquake. The reactor shut down, but then the tsunami took out the generators, and without that cooling of the water being pumped through, the storage containers overheated and then exploded.